This is the Mrs. T Chem Talk review video for acids and bases for Regents Chem. In case you don't know who I am, I'm Mrs. T. I'm a chemistry teacher at Calhoun High School in Merrick, New York. This again is the review video on acids and bases, and you may recognize from class this color in the background. Remember that this is phenolphthalein pink, a color that I often wear during this chapter. I didn't wear it today, I forgot to, but this, remember, is the color that phenolphthalein indicator will be in the presence of a base. First thing we talked about in this chapter was electrolytes, and an electrolyte is going to be any substance that dissolves in water to make a solution that has mobile ions. Once you have mobile ions in solution, this solution will conduct electricity, and the reason why they're called electrolytes is because of this ability to conduct electricity. We measured this with both the vernier probes, and we saw the conductivity on the screen was high for acids, bases, and soluble ionic compounds. Anything that has ions in solution has a high conductivity. We also were able to see that the light bulb lit up for the electrolyte solutions. When we talked about the acids and bases chapter, the first thing we talked about was the metals that will react with acid to release hydrogen gas. This is from your reference tables. This is table J, and table J, sorry about that. Table J gives us what's called the activity series. And when we talk about this activity series, any metal that is higher than hydrogen on table J, any metal from here up will react with an acid to release hydrogen gas. So for example, sodium is here, hydrogen is all the way down here, so sodium is above hydrogen. If we react sodium with hydrochloric acid, the sodium is more active than the hydrogen, so it reacts in a single replacement reaction where it actually kicks the hydrogen out of the compound. The sodium becomes an ion, and the compound becomes sodium chloride, that product, and then the hydrogen comes out of the compound and is released as hydrogen gas. We also have some common acids table on, we're going to have this on table K. So this is just a list of some common acids, and what we're going to notice is that for most of these acids, the first letter in the formula is going to be an H. The other possible format that you're going to see for something to be an acid and recognize it is that the last four letters will be COOH, and that's an organic acid. So something that has C's and H's in the front and then ends in COOH is also an areneous acid. So an areneous acid is something that has H+, or also known as H3O+, as the only positively charged ion in solution. They tend to have a low pH on our pH scale, which is measured at 25 degrees Celsius. They're going to be lower pH than the neutral value of 7. And the concentration, remember these brackets mean concentration, of H+ is greater than the concentration of OH-. And since we talk about H+ and H3O+ in an equivalent fashion, we could also say that it's H3O+ is greater than OH- concentration. Remember, we called this one the hydrogen ion, and we called this one the hydronium ion. So if they mention hydrogen ions in solution or hydronium ions in solution, we're talking about acids. For indicators, the main indicators that we talk about are litmus and phenolphthalein. And for litmus, in the presence of an acid, you're going to get litmus to be red, and for phenolphthalein, in the presence of an acid, will show the colorless solution. So it will not change color in the presence of an acid. By contrast, bases, we have some bases on table L, and for our bases on table L, we notice that it's usually a metal with OH at the end. Ammonia is an exception. Sometimes when we have N's and H's together at the end of a formula, that's also a base, but ammonia is the one that we have to remember like this. Otherwise, it's going to be a metal in front of OH or a metal with OH in parentheses and some number outside of here, like a 2 or a 3. If we have something that's not a metal in front of OH, that's not going to be a base. So again, an Arrhenius base is usually a metal plus OH. It has OH minus as the only negative ion in solution. We're going to have a relatively high pH for a base solution. It's going to be, which again is neutral on our pH scale that's measured at 25 degrees Celsius, and the concentration of hydroxide minus ions will be greater than the H plus or the hydronium. Remember, this OH minus is called hydroxide. We can find that formula on table E in case we're confused about that. For litmus and phenolphthalein, in the presence of bases, litmus, remember, is going to be blue, and phenolphthalein is going to be that bright pink, like this color and this color of the font. This is all phenolphthalein pink on this particular slideshow here, on this particular video. When we talk about the alternate theory, I'm going to move this back over here. When we talk about the alternate theory, we're going to be able to define acids and bases as Arrhenius acids and bases for the previous slides. But the Bronsted-Lowry theory, we are just going to call the alternate theory for our purposes. And for the alternate theory acids, it's an H plus proton donor. And for a Bronsted-Lowry base, it's an H plus proton acceptor. Anything that has extra H's can donate them and act as an acid. Anything that needs H's can accept them and act as a base. For example, if we wanted to do a Bronsted-Lowry acid-base reaction, in order to find what are called the conjugate acid-base pairs, we're going to kind of bracket species that have a same common ending usually. So HCl and Cl minus, H2O, and H3O. Then we look among the pairs and look for which one of the ones that we connected has more H's. The one with the extra H is going to be labeled as our donor acid. The one with the less H's is going to be labeled the acceptor base. And for H2O and H3O, H3O has the extra H, so it's my acid of the pair. H2O is acting as a base. So in this reaction, an H from HCl is given to H2O. H2O turns into H3O plus, and HCl turns into Cl minus. For another example of a Bronsted-Lowry or alternate theory reaction, I have ammonia or NH3 put into water, and the NH3's conjugate, which has to be on the other side of the arrow, is NH4 plus. H2O's conjugate is OH minus. These two both have O's. These two both have N's. That's how I know that they're conjugates. I look among the pairs. Whichever one has more H's is the donor acid, so that makes NH4 plus the acid of the pair, NH3 the base because it has 3 H's versus 4, H2O versus an understood 1H, that makes OH minus the base of the pair, and H2O an acid. Now you may have noticed in the last two slides, in one slide water acted as an acid, in the other slide water acted as a base. So we're going to talk about that on the next one. And I'm going to show you that water can actually react with itself, and it does this in solution. So if I connect one of the waters with OH minus and one of them with H2O, make these my conjugate pairs, in this conjugate pair that I arbitrarily picked which one it went with, H2O over here has an extra H, OH minus has one less. Here, this H2O has one less than its partner. H3O has one more. What I should notice is that water can act as either an acid or base. We call this amphoteric or amphiprotic, and that's going to be something that can act as either an acid or a base, and water does a good job of that. So something that has H's to donate but also has the ability to accept H's is called amphoteric or amphiprotic, and this happens in pure water, and this is why all water-based solutions have both H3O plus and OH minus, because when water autoionizes or water exchanges H pluses with itself, we make these ions in every solution. So it's the ratio of the H3O and the OH minus that tells us whether a solution is going to be acidic or basic. So when acids and bases combine, when acids and bases combine, I don't want to leave the question there covered up, we have a neutralization reaction, which is a special kind of double replacement where my outers come together and my inners come together. For neutralization, once I identify that there's an acid plus a base, my first or one of my products is always water, because the H goes with the OH, the H from the acid goes with the OH. Then the metal from in front of the base goes in front of the nonmetal from the acid. We crisscross and drop the signs to get the formula. K now goes in front of NO3. They have a +1, -1. And Li goes with SO4. Li has a +1, but SO4 has a -2, so that's Li2SO4, which means that for this one, I'm going to just erase a little bit so you can see this a little bit better. We actually have to balance the equation after the fact. So to get 2 Li's on each side, I put the 2 there. That's 2 H's, 2 Li's, 2 OH's. That means I'd also have a 2 in front of the H2O. But the most important thing to note is that whenever you have an acid with a base, we know these are acids because they start with H. We know these are bases because it's a metal with OH. One of our products will always be water. The other product comes from the pieces that are left from the acid and the base. When we do a titration, we do this in order to find out the concentration of an unknown acid or an unknown base. And we have a formula on table T that says MAVA equals MBVB. I also caution you to multiply by the number of H's if in the formula of the acid if there's a subscript, for example, in H2SO4, or to multiply by the number of OH's if there is a subscript after the OH, like MgOH2, you would then have to multiply by 2. But you'll recognize the question because it'll say something like how liters of 4 molar NaOH are required to completely neutralize 50 milliliters of 2 will be connected by the word of. So how many milliliters of 4 molar? That means that the 4 molar goes on the side of the X. These happen to be the base numbers, so that's why I put them on the right, but it doesn't matter which side you put them on. To completely neutralize 50 milliliters of 2 molar HNO3, those are my acid numbers. And then I'm going to just figure out my math. And my X comes out in milliliters, and it came out to 25 milliliters when I did my math. So we're going to use a setup like this with burettes. We will put some acid in here, usually with the indicator phenolphthalein, and then we'll add base until the color changes to this nice phenolphthalein pink. We will read the burette by kind of turning our head to the side so that the lower number is by our left side and the higher number is by our right side, because remember, these are numbered like a ruler. You read the leading edge, which is the bottom of the meniscus, and you're going to take your final values for each burette and you're going to subtract to get the volume used. When we talk about the meaning of pH, the meaning of pH is actually negative log of the H+. So if we look at the pH scale, usually high on the pH scale would be considered 14. 14 till just above 7 is considered base. 7 is considered neutral, and lower than 7 is considered acid. Remember that for base, we have both OH minus and, H3O plus, but the OH minus is greater. At neutral, OH minus and H3O plus are equal to each other. And when we have an acid, it's the H3O plus, which is greater than the OH minus concentration. The pH scale is a logarithmic scale, which means that every number on the pH scale is a factor of 10. So if we want to talk about how the pH changes as we raise it or lower it, we can do that. If we add base, the pH will go up. If we add acid, the pH will go down. And so we're starting here, and we're saying that we're starting with a pH of 5, and we add agricultural lime. So as we add this agricultural lime, the pH is either going to go up or down. Now, it says that the soil underwent a 100-fold decrease in hydronium ion concentration. Sorry about that sloppy circling there. So it decreased the hydronium. If we are decreasing hydronium, we are getting less acidic, and 100-fold, the number of zeros, tells us that we're moving 2 places on the pH scale. So if we're getting less acidic, that means that the pH is going up, and my new pH would be 7. Because remember, this is hydronium. If we're decreasing hydronium, we're getting more like a base. Anytime they give you a 100-fold, a 1,000-fold, a 10-fold change in pH, the number of zeros tells you how many places to go up or down on the pH scale. You use the change in which kind of ion to decide whether the pH will go up or down by that many places. When we look at table M, we have some various indicators. If we look at this, for example, methyl orange changes from red to yellow here in this range. That means that we have orange in the middle. So that means that before a pH of 3, the color of that indicator is red. From 3.1 to 4.4, the pH of that indicator is orange, and at 4.4 and after, the pH is going to be yellow. So what we can do is, if we know that a pH is less than 6, we would look at the earlier numbers. For example, for bromethymol blue, less than 6 would be yellow, more than 7.6 would be blue, and this center range in between would be green. So if we look and we say a solution starts as an acid with a pH of 4, a small volume of NaOH is added, and the hydronium ion concentration is reduced by 100 times. That means if we're getting less hydronium, we're getting more basic, so the pH is going up. 100 times, 2 zeros tells me to move by 2 places. Find the new pH. My new pH is 6, and the color brome creasel green will be. So brome creasel green is yellow before 3.8, blue after 5.4, and green in the middle. This pH is after 5.4, so this will be a blue color in brome creasel green. This is the end of the review for acids and bases. If you have any questions, please feel free to come to my extra help. If you're not one of my students, you can certainly watch the video again, pause, rewind, watch different sections that you need more help with. So hope everyone's doing well. Have a good day.